In this video, I will show how to analyze the first derivative of a function to find its relative and absolute extrema values, and how to use the second derivative to find the function's inflection point, if any. So let's start with the analysis of the first derivative. The first derivative in this case is 6x squared minus 12x, and to find the critical values we have to set the function equal to 0 or find the points where it doesn't exist. So the best format to write the polynomial function to analyze it is the factored form. So I'm going to factor out 6x, x minus 2, and now I'm going to set it equal to 0 or find the values where it is not defined. Since it's a polynomial function, it's defined everywhere, so I'm not going to get anything out of this part, but setting it equal to 0 gives us the following solutions. So x equals to 0 or x equals 2. So these are the critical values. 0 and 2. Next, we construct the sign chart for the derivative of the function. On the sign chart, we put all the points where the function or where the derivative is equal to 0 or does not exist. And then we draw the sign chart. So here the derivative is positive to the right of 2, negative between 0 and 2, and positive to the left of 0. And these signs we interpret the following way. Where the derivative is positive, the function is increasing. Where the derivative is negative, the function is decreasing. And where the derivative is positive again, the function is increasing. This means that we have a relative max at 0 and relative mean at 2. So we can find f of 0. F of 0 is 0. So 0 is a relative max. And f of 2 is 16 minus 24, negative 8 is a relative mean. To find the absolute minimum and maximum, we have to compare every relative mean and max that we found with the value of the function at the end of the domain. So in this case, domain is from -1 to infinity, and we set up the following table. So we're going to find the value at -1, 0, 2, and infinity. So f of -1 is -8. F of 0 we found to be 0. F of 2 is also -8. And f of x at infinity cannot be evaluated, but instead we find the limit of this function. So the limit of a polynomial at infinity is just the limit of its leading term, and this power function with a positive leading coefficient goes to infinity as x goes to infinity. So the function goes, the original function also goes to infinity. And now we have to compare all these values with one another. So -8 is the smallest one, then goes 0, and then we have infinity. Since infinity is not the value, that means we interpret that as the absence of absolute max. But we have one absolute mean, which is -8, which is obtained by the function at two different points, f of -1 and f of 2. So the absolute mean is 1, but it happens at two different points. So this is how we use the first derivative to find the relative and absolute extrema values. Now, to start the second derivative analysis, we have to find the second derivative first. So the second derivative is 12x minus 12. And again, to find the potential candidates for points of inflection, we have to set it equal to 0 or find where it doesn't exist, and the best way to write the polynomial function is in factored form. Again, since it's a polynomial, it exists everywhere, so there's no such point where it doesn't exist, but setting it equal to 0 gives us the following value, x equals 1. So it's a candidate for inflection point. Then we set up the sign chart for the second derivative, for which we use all the values where the function is equal to 0 or does not exist. And looking at this function, we know that to the right of 1 it's going to be positive, to the left of 1 it's negative, and then we interpret these signs as the following behavior of the function. When the second derivative is negative, the function is concave down. When the second derivative is positive, the function is concave up. Since at 1 concavity changed and 1 is in the domain of the function, we say that 1 is the inflection point, and we can find the value of the function at 1. It is -4, and it's the only inflection point. We can also use the second derivative to classify the critical values. So for example, at 0, the second derivative is negative. That means if 0 is a critical point with a negative second derivative, it has to be maximum. And same thing for 2. At 2, the second derivative is positive, and that means that at 2 we have relative minimum. So this is an example of how to use the first and second derivative to learn something about the function.